Hash, right? Okay, I guess I'll get started. A bunch of people are here who know this, so. The homework for number 6 for chapter 7 is due on the 23rd. That's next week, Wednesday. We're gonna finish chapter 7 today, so you should have plenty of time to finish it. So, and the tests are pretty much graded. I need to do one last sweep through just to check if I made any mistakes or such. The grade should be up tonight, but in general, you guys did well. Like the majority of the class got in the 90s. But no. So that was good. I should have the grades up by tonight. I just really want to do at least one or two more, look through my grading, see if I made any mistakes when I was grading things last night. Um, so yeah. Let's look at work done by a constant force. So the work done by a constant force As we mentioned before, work is force times distance times the cosine of the angle between them. Strictly speaking, in linear algebra terms, or in like vector terms, work is force dot displacement or distance. It's a dot product, but that ends up being the magnitudes times the cosine of the angle between them. And then the work energy theorem relates work and kinetic energy. Delta K is the total work, and that is going to be 1/2 mv final squared minus 1/2 mv initial squared. Kinetic energy is 1/2 mv squared. So we can talk about work in terms of its change in kinetic energy. So here is an example: a 4.1 kilogram box of books is lifted vertically from rest a distance of about 1.6 meters with constant upward applied force of 52.7 newtons. Find the work done by the applied force, the work done by gravity, and the final speed of the box. Back in a minute. Okay. Okay. So let's part A. You want the work done by the force. That's the force times the distance times the cosine of the angle between them. Well, force is 52.7 newtons. Distance is 1.6 meters, and it's the cosine of 0 degrees. Which is 52.7 times 1.6. 84.32 new joules, which you would round to 84.3 joules. Then let's do the work done by gravity. That's the force of gravity times distance times the cosine of the angle between them. Force of gravity is mg, so that's 4.10 kilograms times g, 9.80 meters per second squared times 1.6 meters times the cosine of 180 degrees, because gravity and the distance are in opposite directions. So this comes out to 4.1 times 9.8 times 1.6 times -1 minus 64.288 joules, or minus 64.3 joules. The total, the final speed of the box, well, it started at rest, so the total work is going to be the change in kinetic energy, so that's just going to equal 1/2 mv final squared, because the initial kinetic energy is 0. So our total work is going to be 84.3 plus negative 64.3. 20 joules. That is 1/2 mv squared. So v is square root of 2 times 20 joules over 4.10 kilograms. So velocity is 3.12. Yes. 0. 0 degrees.
So is the work on the side part C?
Oh, yes, this is part C. So the total work is going to equal the final kinetic energy of the box, because it starts with 0 kinetic energy. And so that'll let us find the final speed of the box.
The equation on part C, 1/2 mv squared g. What was it, 1/2 mv?
7 mv final.
Okay.
Basically this, except I dropped this last term because the initial velocity was 0.
Oh.
1/2 mv squared. Yes, 2 times 20 joules. 20.0 joules. Let's have this down. It is in your book, so. So here, when a father takes his daughter out for a spin in a stroller, he exerts a force with a magnitude of 44 newtons at an angle of 32 degrees below the horizontal, as shown in the sketch. The stroller and the child together have a mass of 22.7 kilograms. How much work does the father do on the stroller when he pushes it through a horizontal distance of 1.13 meters? And if the initial speed of the stroller is 1.37 meters per second, what is the final speed, assuming the stroller rolls with negligible friction? So we were having that number 5 minutes a second. So, start by finding the work. Work is force times distance, times the cosine of the angle between them. So that the force is 44.0 newtons. The distance is 1.13 meters, and the angle between them is 32 degrees. So cosine of 32 degrees. And that comes out to a work of 42.2 newtons. That's part A. Part B. Well, change in kinetic energy equals the work. So kinetic energy final minus kinetic energy initial equals work. So kinetic energy final equals work plus kinetic energy initial. So that's 1/2 mv final squared equals work plus 1/2 mv initial squared. And you can do this in a couple ways. The way I did it first was I just found the final kinetic energy on the left side, and then I solved for the final velocity. Your book solves it by the equation, but this is 42.2 joules plus 1/2 times 22.7 kilograms times 1.37 meters per second squared, which comes out to 3.5 joules. That equals 1/2. So the final equals square root 2 times 63.5 joules over the mass 22.7 kilograms. And that comes out to a final speed of 2.37 meters per second. This is square root of 2 times kinetic energy over mass. Oh, because for my other class uses different, the textbook uses different notation. Any questions about that?
It equals 2K over.
Yeah, so because 1/2 mv squared equals kinetic energy, so this is kinetic energy final. So 2 times this is K final. So 2 times K final over M equals the final velocity, square root. So that's just 1/2 mv squared being solved for velocity. So here, if you have a certain car, to accelerate a certain car from rest to the speed v, requires the quantity of work W1. Oops. I just wanted to check something. Okay, that's all. As shown in the sketch, the work needed to accelerate the car from V to 2V is W2. Which of the following statements is correct? W2 equals W1. So we start at some velocity 0. We end at some velocity V. And then we do some more work and we end up at some velocity 2V. So which of the following statements is correct? W2 equals W1. W2 equals 2 times W1. W2 equals 3 times W1. Or W2 equals 4 times W1. And which of these do you think is the best explanation? The increase in speed is the same, so the work is also the same. To double the speed requires double the work. Kinetic energy depends on V squared, and hence it takes 4 times as much work to increase the speed to 2V. 4 times as much work is required to go from 0 to 2V as to go from 0 to V. Therefore, the work required to increase the speed from V to 2V is 3 times the original work. Which of those do you think is the best explanation? Oh, yeah. Yeah, that's wrong. Well, this is 2 times V is the final velocity. Twice V. That's close. It's actually, oh, you're saying option 4 here? Yes, that's right. Which is that work 2 equals 3 times work 1. Because it takes 4 times as much work to go from 0 to 2V as it does to go from 0 to V. Because the work required is basically 1/2 mv squared. And the difference from V to 2V, you can think of it, this is 2V squared minus V squared, which gives you 3 times V squared. So you get 3 times work 1. So this last one is the correct answer. And work 2 equals 3 work 1. That's the correct answer. It's third one on the list, but it's the fourth one on the list of the explanations. So the first one is work 1 equals work 2. The second one is work 1 equals, sorry, work 2 equals work 1. The second one is work 2 equals 2 work 1. The third one is work 2 equals 4 work 1. And the last one is work 2 equals 3 work 1. Yeah, the kinetic energy at the end is 4 times the kinetic energy at the start, but the difference between 1 and 4 is 3. Okay, so that was work. Let's talk about how we can talk about work done by a variable force. So we were talking about work done by a constant force. Well, if work is done by a variable force, a force that changes, it's basically the integral over force times distance, assuming force and distance are in the same direction. You can also include the angle So if a force is constant, we can interpret the work done graphically as basically a rectangle. If the force takes on several successive constant values, you can do it as several rectangles. You know, do the work here, then the work here, then the work here, then the work here. And so you can approximate a continuously varying force by a succession of constant values. This is an integral. You guys are in calculus, right? Yeah, or have taken it. It's just the integral. So essentially, if force varies, work is just the integral of force times distance. It's the integral of what is it? It's force dot dx from x initial to x finite. And it's a path integral. I can't remember the symbol for off the top of my head. But so the calculus definition of work is the integral of f dot dx. If f is constant, you just get f dot d, which is force times distance times the cosine of angle. If x changes in magnitude with x, work is the integral from xi to xf of force times cosine theta times dx. So the example we're going to talk about is a spring, where for a spring, force is minus kx. So work ends up being, the integral of minus kx dx from kx initial to x final. So this is a spring. So the force needed to stretch a spring. So this is the work done by a spring. The work done on the spring will be force on the spring is just going to be kx. So the work done on the spring is 1/2 kx squared. The work done by the spring is minus 1/2 kx squared, going from 0 to x. The force needed to stretch a spring on x is kx. Therefore, the work done in stretching the spring is 1/2 kx squared. That is the work you have to apply to the spring. That's this calculation here. If you want to work out the work the spring did, it ends up just being minus 1/2 kx squared. Depends what you're talking about. This is the work you did stretching the spring. This is the work the spring did resisting your stretch. I was saying by the spring as opposed to on the spring. Yeah. I mean, this is, strictly speaking, this is the work done by the spring. And this, I guess, would be the force on the spring or the force applied. So the work applied would end up being 1/2 kx. So the minus is the work done by the spring. The plus is the work done by you on the spring. So this is the work you did. This is the work the spring did. And this ends up being the amount of energy that gets stored in the spring. But we'll get to that in the next chapter. So there's some funky things with signs here that can be a little confusing. But in general, if you want to figure out how much work it takes to compress or stretch a spring, that is the work to move the spring. This is the work you have to apply. If you want to figure out how much work the spring did, it's minus. So this is the work to stretch the spring. So the work required to stretch the spring. So here, if we have a toy snake, it has a spring with a force constant of 230 newtons per meter. How much work is required to stretch the string to 2.5 centimeters from equilibrium?
So would this be the bottom equation?
This would be this one. This will be the positive.
Yeah, the positive.
So this is the work required, as opposed to the work done by the spring. The toy spring snake will do an equal and opposite amount of work. Because in the end, nothing's moving. On the spring constant. So in this case, K will be 230 newtons per meter. Yes, in meters. Yep, it's 0.072. That's for part A. So joules, it's work. So the work applied to the spring is 1/2 kx squared. So that's going to be 1/2 times 230 newtons per meter times 0.025 meters squared, which comes out to 0.072 joules. And for part B, we have the spring in a car suspension has a force constant of 21,000 newtons per meter. If 3.5 joules of work is done on it, how far is it compressed? Yeah, you're solving for X now. 1/2. Yep. So you end up with, so same equation, but here you end up with x squared equals 2 times work over k. So x equals square root of 2 times work over k. And then you can just plug in the numbers. So square root of 2 times 3.1 joules over 21,000 newtons per meter and we will get 0.017 meters or 1.7 centimeters. So it's a perfectly reasonable way to do it. I just tend to rearrange things in variables first. Maybe there's a rounding error in there or something, but because it should still boil down to 2 times 3.1 divided by 41,000, and then the square root of that. So if you had 2 times, so you would have had like 1/2 times 21,000, which is 10,500, and then divide 3.1 by that, which is a little number, and then you end up taking the square root of that. That would do it. Did I type 3.1 in my calculator? So I put the wrong number in my calculator. 3.5 is what it says there. And that would be 1.8. And yep. Okay, so you did it right, and I misread this. You put 3.1 by accident. You didn't do anything wrong. I did. Oh, didn't get enough sleep. Yes, it's 1.8. And that matches what's in the book. So this is a spring. So the work done on a spring is 1/2 kx squared. It's the easier one to deal with because it is negative. It's usually what you care about. How much work are you doing to the spring to compress it? Because when you want to talk about how much work you get from the spring, you end up being more interested in talking about potential energy, which we'll get to in next time. Potential energy stored in the spring is also 1/2 kx squared. You'll find out. Okay. Because it's potential energy stored by the spring is minus the work done by the spring, so it gets rid of that minus sign. But I'm not, for spring problems, I'm not going to be super picky about signs. Just, there'll be an obvious way that things should go. And you should be able to work it out. Here, the work required to deflect a typical atomic force microscope cantilever by 0.1 nanometers. 0.1 nanometers. This is 1.0 times 10 to the minus 10 meters. Is 1.2 times 10 to the minus 20 joules. What is the force constant of the cantilever? Treating it as an ideal spring. And how much work is required to increase the deflection of the cantilever from 0.1 nanometers to 0.2 nanometers? The appropriate equation, work is 1/2. Kx squared. At least for part A. Oh, wait, no, that's not right. Where? Um. Yep. So K ends up equaling 2 times the work over x squared, which is 2 times 1.2 times 10 to the minus 20 joules over 1.0 times 10 to the minus 10 meters squared. So you get 2 times 1.2 times 10 to the 20 joules over 1 times 10 to the minus 20 joules, 10 to the minus 20 meters. The 10 to the minus 20s cancel, and you're left with 2.4 newtons per meter squared. Newtons per meter. And then the work to go to 0.2 nanometers. So the work for 0.2 nanometers. Yeah. To do that, you just, well, you just plug it in, it's 1/2 kx squared. You can do 1/2 times 2.4 times 2 times 10 to the minus 10 meters. And you will end up with 4 times the initial work. So that will be 4.8 times 10 to the minus 20 joules.
That equals 4 times 2 times 10.
So yeah, that should be a square there. So because it's x squared, to double the distance takes 4 times the work. So it ends up just being 4 times this. And then here we have a block with a mass of 1.5 kilograms and an initial speed of 2.2 meters per second. And it slides on a frictionless horizontal surface, and the block comes into contact with the spring that's in the equilibrium position, and compresses until the spring comes to rest momentarily. We want to find the maximum compression of the spring, assuming its force constant is 475 newtons per meter. The work done by the spring is minus, well, in this case, you can use the minus 1/2 squared. And then we can set that equal to the change in kinetic energy. Okay. Which will be negative. So the work done by the spring will end up equaling delta K, capital K as opposed to lowercase k. So too many things use K. Delta K equals work. So we have minus 1/2 kx squared equals 1/2 mv final squared minus 1/2 mv initial squared. Our final velocity is 0, so this term goes away. And so we get minus 1/2 kx squared equals minus 1/2 mv initial squared. These cancel. We want to find x. X squared equals mv squared over k. So x equals square root of mv squared over k. X equals square root of mass is 1.5 kilograms times 2.2. Well, actually, you can even pull out square root of m over k times v, but 2.2 meters per second squared over 475 newtons per meter. How does the book do it? Okay, so they found, the book found delta K and then just did 2 times delta K over lowercase k. So this is lowercase k. Problems that have 2 versions of K. Sorry about lack of clarity. And normally, my own tendency for writing kinetic energy is I usually write E kinetic. But this is how the book does it, with a capital K. Yes. And this is square root of mass over K, which is 475 times the velocity. And this ends up being 0.1 book does it slightly differently. Let's see if I got a different result. Nope, we got the same thing. 0.1, sorry. And once we finish chapter 8, we'll learn a much easier way to think about this. It'll give you the same answer in a less confusing way. Because we'll have introduced potential energy and we'll just talk about the kinetic energy being turned into potential energy and end up with the same equation, but conceptually easier to think about. Any questions about this? Okay, let's talk about power. Power is work over time. Strictly speaking, power is the time derivative of work, like velocity is the time derivative of position. You know, it's the time derivative of energy. It's how energy moves. So power is work over time. The unit for power is the joule per second, or the watt, named after James Watt, who made steam engines better, and was very good at selling them. In order to help sell them, he invented a unit called the horsepower. 1 horsepower. So 1 horsepower is 746 watts. Roughly. Strictly speaking, it's 550 foot-pounds per second. That's exactly what a horsepower is defined as, because it's actually an imperial unit. But a horsepower is not the power exerted by a horse. A horsepower is the average power you get out of a horse over a day, as told to you by James Watt, who's trying to replace your horses with a steam engine. Now, this is a unit that was invented for advertising. It does, you know, horses can actually output something like, I don't know, I watched something where they actually hooked a horse up to a dyno and got like 6 horsepower out of it. Short term. Oh, that was short, but it was a draft horse, but it got generated 6 horsepower over a short period of time. To be fair, James Watt was talking about the energy you got out of a horse, you know, the power you got from a horse on average. So, you know, when the horse isn't working, you know, the average amount of work you can get out of a horse over like a day. And he wasn't awfully far off, but I mean, there was, I don't know. He was never very open about his calculations for how he generated it, but he went somewhere that were actually using horses and put some numbers together. But, you know, it's the average you get out of a team of per horse out of like a team of horses over a day kind of thing. So the horse takes breaks and stuff in there. But some typical values of power in watts. You may be used to using watts for measuring power on all kinds of electrical stuff. Because electrical stuff, it's easy to calculate power in watts, because that's how because all the electrical things are in the SI units. So for example, the Hoover Dam pumps out about 1.34 times 10 to the 9 watts. That's 1.34 gigawatts. Yeah, gigawatts. A car moving at 40 miles per hour uses about 7 times 10 to the 4, 70,000 watts. A home stove is about 12,000 watts, 1.2 times 10 to the 4. Sunlight falling on 1 square meter is about 1,380 watts. A refrigerator uses on average about, okay, a refrigerator when it's running uses about 650 watts. If you have a decent refrigerator, the average over the day is going to be less than that. Yeah, I think that number is about right. Refrigerators are weird because they're like on part of the time and off part of the time. So sometimes those numbers there, and that might be a little dated. Television uses around 200 watts. A person walking up the stairs has about uses about 150, uses about 150 watts. The human brain uses about 20 watts. So if an object is moving at constant speed and the force of in the face of friction, gravity, air resistance, whatever, it turns out because power is work times time and work is force times distance, power ends up being the force required times the velocity you're traveling. So if it takes like 100 newtons to travel at 10 meters per second, you're going to be using 1,000 watts. So power is work over time. You can write that as force times distance over time. You end up with force times velocity. So that's if you're moving at constant speed in the face of various forces, you end up with force times velocity. So here, to pass a slow moving truck, you want your fancy 1.3 times 10 to the 3 kilogram car to accelerate from 13.4 meters per second at 30 miles per hour up to 17.9 meters per second, 40 miles per hour, in 3 seconds. So what's the minimum power required for this pass? Remember, work is change in kinetic energy, and power is work over time. Yeah. You find the work and divide it by the time. So work will be 1/2 mv final squared minus 1/2 mv initial squared. That's going to be 1/2 times 1.3 times 1/2 times 1.3 times 10 to the third times 17.9. Let's go down per second squared minus 1/2 times 1.3 times 10 to the third times 13.4 meters per second quantity squared. So this can actually be written as 1/2 times 1.3 times 10 to the third, and then you just do 17.9 squared minus 13.4 squared in parentheses to speed it up a little. So this comes out to 9,155.2.5 joules, and power is work over time. So 9,155.2.5 joules over 3.0 seconds gives you 30517.5 watts, or 3.05 times 10 to the 4 watts. Which is about 40.9 horsepower. So it's a perfectly reasonable thing for a car to do. Doesn't take a lot of power, car-wise. But thinking, there are definitely some cars out there that wouldn't have that much horsepower. And it requires some to maintain your speed, but that's the minimum additional power. Now, that's the minimum power required. And if you're working, so, and here's an example where if you're working against a force, if it takes a force of 1,450 newtons to keep a car moving, a 1,300 kilogram car moving with constant speed up a slope of 5.25 degrees, if the engine delivers 4.1 times 10 to the 4 watts, 55 horsepower to the wheels, what's the maximum speed of the car up this hill? This is fairly straightforward. Power is work over time, so that's force times distance over time, so that ends up being force times velocity. We know the force required, we know the power. So the velocity ends up being power over force. So that's 4.10 times 10 to the 4 watts divided by 1,450 newtons which gives us a velocity of 28.3 meters per second. That's going to be maximum speed of the car. Up the hill. It turns out you don't need the mass, you don't need the angle, you just need the force and the power. Any questions about that? Okay. That is it for today. That's the end of the chapter. So, work is force times distance times cosine theta. If the force is constant and parallel to the displacement, work is force times distance. Total work is the work done by the net force. It's also the sum of all the works done by the individual forces. So sometimes it can be easier to do one, sometimes it can be easier to do the other. The SI unit of work is the joule. That is a kilogram meter per second squared, or Newton meter. Total work is equal to the change in kinetic energy. So delta K, where kinetic energy is 1/2 mv squared. So delta K is equal to the total work, which is 1/2 mv final squared minus 1/2 mv initial squared. The work done against a spring force is 1/2 kx squared. And power is the rate at which work is done, work over time. The SI unit of power is the watt. Under certain circumstances, you can simplify work over time to be force times velocity. Yeah, basically have to have constant velocity and yeah. So that is all for today. I'll get your grades up on the tests later tonight. I just want to do one last scan through, and I haven't entered the grades yet, so yeah. That will be all. See you on Wednesday.